Okay, so what we're looking at here is number 6 from the 2021 BC exam. It's a Taylor series, as it normally is for number 6. There's some slightly different things in this problem and some things that we've seen before, so let's just jump right in. So we've got a function f has derivatives of all orders for all real numbers. The Maclaurin series for g given by g of x is equal to, and then they've got our summation, as well as its general term on its interval of convergence. So we've got our general term right here, which is going to help us a lot in determining a bunch of different things. So the first thing it says is, state the conditions necessary to use the integral test to determine the convergence of this series, which is kind of weird that we're determining that, considering what we got going on here, but we'll come back to it. Now, in order for us to use the integral test, what we have to do is we have to say, okay, this right here needs to look like this particular function. In other words, we replace the n with x, and then we do the integral from 0 to infinity. That's the integral test, but this function right here has to be continuous, positive, and decreasing the entire time on the entire interval in order for us to use the integral test. All of those things are true about that particular function. So now we can say if this is a convergent integral, in other words, I can actually find the value, then the series is going to be convergent as well, although they will not be the same value. Well, I can take the antiderivative of this by just making it e to the negative x real fast. So the antiderivative of that is e to the negative x divided by negative 1, and we're going to go from 0 to infinity. In order to evaluate that, I do have to change that to negative 1 over e to the x. I plug in my infinity, so I get negative 1 over infinity minus negative 1 over e to the 0. This first part is going to be 0 minus e to the 0 is 1, so what I really have here is plus 1. So I got that the integral is indeed convergent. If that integral is convergent, then that means that the infinite series must be convergent as well, since I got a number right there. Okay, since that exists, then we know that the series that looks the same is going to be convergent. Those are the steps necessary to use the integral test. Letter B says, use the limit comparison test with this to show that this particular series, when I plug in 1, converges absolutely. Well, remember, to converge absolutely means that I am going to converge, this series is going to converge based on the fact that I want to see if it converges without the negative. So what I'm really saying is I'm going to compare this series right here to 1 over e to the n. Now the limit comparison test has us taking the limit as n approaches infinity of one of those functions over the other one. And it doesn't matter which one goes on top and bottom. I just need to make a fraction out of both of them. And as long as I get a number, I do the absolute value, that's not going to matter here. As long as I get a number here, then I'm going to say, oh, that is a convergent series. So when I do this, I flip that upside down, and then I take the limit as n approaches infinity, and you'll notice that I've got an e to the n on the top and the bottom, so this becomes 1/2. Because that number is greater than 0, but it's an actual number, we just use the limit comparison test to show that this series converges absolutely. And again, the key was to show absolute convergence, we had to get rid of the negative right there. Letter C says determine the radius of convergence, which means I have to do the ratio test. So I'm going to do the limit as n approaches infinity of the n plus 1 term, so I get negative 1 to the n plus 1, multiplied by x to the n plus 1, over 2e to the n plus 1 plus 3, divided by negative 1 to the n, so just by the general term itself, x to the n, over 2e to the n plus 3. And it's the absolute value of that, and it needs to be less than 1. Well, in order to do this, we're just going to have to flip that bottom fraction upside down, and then we're going to times them together, and the absolute value is still there. I'm not going to write it for just a second, because we need to see what cancels out inside of the parentheses, 2e to the n plus 3 over negative 1 to the n times x to the n. So everything but one negative n crosses out, everything but one x crosses out, and then this is the limit as n approaches infinity. Now here you've got to be a little bit careful, because what's happening on the bottom here, this is really 2e to the n times e. So in reality, what's going to happen when these cancel out, that 2e to the n and that 2e to the n, when we do the limit as n approaches infinity, those cancel, but I still have an e left over, which is, I've never really seen them do that on a problem like this before, but it's going to be x divided by e. The plus 3's aren't going to matter because we're going to infinity. So I have the absolute value of x over e is less than 1, which means the absolute value of x is less than e. So that is my radius of convergence. E is what it is right here. And again, that one, I'm imagining a lot of people would accidentally forget that there would still be an e left on the bottom. So that is my radius of convergence. The last one says the first two terms of this are used to approximate g of 1. Use the alternating series error bound to determine an upper bound. Now we have to be careful on this one because this series starts at 0. So the first term is determined by taking 0 and plugging it in. The second term is found by taking 1 and plugging it in. So in order to determine my alternating series error bound, I actually have to take 2 and plug that into my series everywhere that I see an n rather than 3, which is kind of confusing. But again, you have to understand that this starts at 0. So negative 1 squared is 1, 2e squared plus 3. I can get rid of the absolute value. And I know that that is at most how much my series is going to be off by. So fairly easy on that last one, if you understood that the series was starting at 0 with our first term instead of 1 like it does on a lot of other series. Hopefully all of those made sense. Again, there was a couple things that are a little bit different, but a fairly straightforward problem if you knew what it was asking you to do. If you have any questions about this one, please let me know.